meant to be ride on lawnmower. Our next quiz is on the 22nd. And really today marks the last lesson of the first unit. So, which is good. I believe we'll start the next unit on the 23rd. I think we'll just use the 21st as maybe a work period to get caught up. And then on the 23rd, we'll start the new unit. Okay, continuity. A function is said to be continuous if it has no holes or breaks in it. Kind of obvious, like it continues on forever. Think of drawing a function where you never have to lift your pencil. These are not continuous. Like this one has a point of discontinuity in it. This one has a break. We're on L6.
So like, do you finish lesson 5 now?
Yeah, we did.
Oh.
Yeah. You okay? You with us? This one we say has a break, like the y values do not connect. And this one has an infinity break where it's headed to infinities around an asymptote. Okay. Is x equals -2, or sorry, f of x equals x minus 2 a continuous function?
Yes.
How come?
Because there's no problems, like you can always go that way.
Absolutely. Every x value, there's no restrictions on the domain. So, yes. And if we wanted to graph that, do you guys remember when graphing linear functions was hard? Like when you were just learning how to do that and it was like, oh, I can't see this.
It was all in COVID. Like I didn't know what's going on.
Yeah.
And later I had to just catch on in grade 10.
That was the time of my life.
Why was that the time of your life?
Domain and range, grade 10.
Yeah.
And never did domain and range in India. It's all I just learned here in grade 11. All the function stuff and all that.
Okay, you didn't do any of that in India?
No, like it's like I did, but not like as functions. We just use equations and all of that.
Right, okay. What about this cubic function here?
No problems.
No problems, no restrictions. So yes, it is continuous.
Ms. Galani, you're the reason why, like a big part of the reason why I'm choosing accounting for
Ooh, that's a career path for sure. That's gonna keep you off your phone for sure. You have to be very dedicated to detail, right?
And like, that's just a job that does like math all the time, right?
Math all day, all the time. Lots of programs, lots of Excel spreadsheets, lots of backwards numbers. It's fun. Well, sometimes things are shown as a negative when really it's money in your account, depending on how it's, yeah. Debits, credits, things like that, yes. Okay, so this little star on the page I put there to remind myself that we're just gonna say that all polynomial functions.
Polynomials, another flashback to grade 9. When Miss D's made me like scared of them and you broke the scaredness.
Oh, Miss Steves was your teacher?
Yeah.
Did she throw you out the window?
She like tried to
Okay, that's fair.
She constantly yelled at me.
What, you? I also constantly yell at you to get off your phone.
That was better back then.
You were better back then?
Yes.
I guess I didn't know Rahat until grade 10, right? So.
Yeah, I remember grade 10 first semester you pulled me out of Machi's class.
What were you doing?
No, then you like made me cry in the office.
I did not make you cry. Your behavior was not okay, and we needed to talk about it.
Yeah.
It was not okay behavior, Allie. That's all I'm gonna say about that one.
That like it looks like.
That I had to pull on the vice principal hat and be like,
Yeah, then you're like, oh my god, like I do not know you at all.
well, because it's not something I would expect from you, Rahat. Not something I would expect from you. Okay, so all polynomial functions, I kind of breezed over that when we were talking about Rahat's bad behavior in grade 10. All polynomial functions are continuous. So that's like your cubic functions, your quartic functions, all that chapter 3 stuff that we did in grade 12 is all continuous. But now we're going to start talking about non-continuous functions or other than polynomial functions. So we have a radical function. We have a rational function. So there is a restriction on the domain for this one, right? We know that the restriction under here is x has to be greater than 2. We know that any number less than 2 will end up being a negative number under the root sign, and we know we can't do that. But this one, because there are no breaks in the actual function, even though the domain is restricted, it is still continuous. It's continuous for x greater than or equal to 2. So we should probably read this note here. Continuity is based on a defined domain of the function. So we know that this one already has a restriction. It's like, hey, it's got to be values greater or equal to 2. It's a defined domain. If the function does not have to exist over all real numbers. So this one can be continuous. The problem with this one is this one's not continuous. 2 reasons. I have a point of discontinuity and I have an asymptote. So this one is a no. The domain on this one is all real numbers except for the asymptote and the point of discontinuity. So because there are breaks in that big domain, we know that it's not continuous. So really anytime you have an asymptote, a break, or a hole, it's a non-continuous function. Okay.
So we would say like the root x minus 2 is
Yes, we would. Yeah. Because my domain is defined by x has to be greater than or equal to 2. And on that domain, on the given domain, it never has a break or a hole or anything in it. So my domain is already, like this is my domain here, and it works in every value in that domain. When I look at this one, my domain is negative infinity to positive infinity, but all of a sudden I got a break, I got an asymptote at.
So basically you left your pants and just over there. That makes more sense.
Yeah. Okay, so if we're going to do it without graphing, we're going to look at this. So we're going to go back to our radical function, and x is equal to 6. Does that work?
Yes.
Yes, so what is it?
2.
Oh, look at you guys. You guys are so fast. 6
But I'm
minus
not
2.
watching real science.
It's amazing. Okay, so what is so there is an actual point that when x is 6, y is 2. And if we were to, oh guys, I've typed this in wrong. This should be a 2. Sorry, that shouldn't be a 6. That should be a 2. Let me just flag that to fix that later. Okay, so Rahat, put your phone down. What's the limit of this function?
2.
Also 2. And I don't have to show the direct substitution. It's the exact same thing as the line above. So if we have a point exists, and the limit is at the same place, if these are the same, we say that the graph is continuous at x equals 6. We're being really specific at that specific point. Graph, maybe I'll say function. So if these are the same, We know that piece of information. Okay, so if we do this one, if we substitute -1 in here, what will we get?
0.
We should get 0. But what else will we get? We won't get 0 as an answer. What are we going to get? We're going to get an indeterminate, right? We're going to get 0 over 0. If we substitute in -1 plus 1, -1 squared plus 3 times -1 plus 2, we're going to end up with 0 over 0. So that's an indeterminate. We know that and we know the difference between indeterminates and undefineds. Indeterminates are zeros on both top and bottom. Now, what is the limit? So we know that something's not existing at that point. So the point doesn't exist. So that's what that's telling me. It says like, there's something that, like it might be an asymptote, it might be a hole, I don't know because I haven't investigated it, but no point exists at x equals -1. I haven't done enough math to say whether it's an asymptote or whether it's a hole. We have the graph above that tells me that it's a hole, but if we didn't have the graph, I'd need to do more math for that. Okay, so what's the limit as x approaches -1? We know if we do direct substitution, it gives us an indeterminate. So what would we do here? Yeah, it is 1 on the graph. How would we do it algebraically? We could do right hand or left hand. I'm going to actually go ahead and simplify. Because if you can simplify, this is the easiest way to do it. Oops. I don't know why I can't write 2 today. I want to substitute anything else in there. Is it plus 2? Okay. So then if I do direct substitution, what's that going to be equal to? 1. So I have no point, but I have a limit. So I have no point exists, but I have a limit, which is good, which indicates to me that this is a point of discontinuity, right? So we know that this graph, this function is not continuous at a very specific point at x equals -1. So the reason why I'm showing you both the graph way and this way, sometimes you won't get the graph, so being able to do it algebraically. So if the point doesn't exist, but you do have a limit, that means there's a hole or a break in the graph, so it's not continuous. Are we okay with that? Does that make sense to everybody? Ali, is that good? Okay. Okay. Okay, I don't know if there's any cut up.
No, there's some good ones.
Okay.
And can you help me make it tomorrow?
Who, what?
Can you help me make a cheat sheet?
Sure. Not right at this very second.
No, but tomorrow it's C block.
Sure.
You help me as well.
Sure. Come on down to the office. We'll do cheat sheets. Okay, if we're going to substitute -2 in, what do I get? We're substituting -2 into that function.
Which function?
The one given right there.
Wouldn't it work with it?
It doesn't work, but what does it give us, Ellie? Does it give us indeterminate or undefined?
Undefined.
Undefined this time, right? Because we're going to have negative 2 plus 1, negative 2 squared plus 3 times negative 2 plus 2. So we're going to have 4 minus 6 plus 2 is 0, so the bottom is going to be 0, but the top is going to be a negative 1. So this time it's undefined. And again, so this time we're not going to negative 1, so we're going to do the limit again for this, and we simplified it before. But we got a different number this time. What happens when I do direct substitution in there? Are you guys okay that I didn't show the simplification? Just because we did it on the other page? So what happens when I substitute in there?
Undefined?
We get that undefined, we get the, we can't do it. So if it's undefined, that doesn't tell us anything about it. So now we got to do left-hand side, right-hand side. So this would give us, if we did direct substitution, that would be 1 over 0. So that means we have to go to left-hand side, right-hand side. Like that's our strategy. Like each one's telling you, oh, I hit a roadblock here, now I got to move on. So we have no point defined, and now we've got to figure out if we've got some value here. So I'm going to look at the left-hand side. So I'm doing the limit as x approaches negative 2 from the left-hand side. So 1 over x plus 2. So that's going to be 1 over a very small negative number. Right? You guys would agree with me? Like if I picked negative 2.01, it's going to be like a really small negative number. So that's going to be negative infinity. This is the ish math that we did for L5. And then if we look at x approaching negative 2, but this time from the right-hand side, we're going to have 1 over a very
Small negative number.
positive this time. Because this one, I might put in 1.99 maybe. This one, I'm going to put in negative 2.01. Like, you know, when I'm thinking of numbers, it's, I don't know, sometimes it's helpful for me to see it on a number line or write down the number that I think I'm substituting in there, just so that helps.
Scallion,
Mm-hmm.
if for the upper, when you look at the left-hand side, you substituted in like a negative 2 points, like something very
Mhm.
close to negative 2, then how come for the, when you do the right side,
Mm-hmm.
you put in a positive?
I didn't. I put in a negative. I apologize.
Oh, but the negative gave us a, oh, okay, that's.
Because you took negative 1.99 and added 2 to it, then you get a really, really small positive number.
Then you get to positive infinity.
Because 1 divided by a really, really small positive number is going to be headed towards infinity. The numbers are just going to get bigger, right?
Got it now.
So what do we know? We know that an asymptote is happening here. Right, so that's what that information told us. So we don't have a point and we have an asymptote. So is the graph continuous?
No.
Not continuous.
Miss Callion,
Mhm.
do you need a character so when you determine it or not define?
Sorry, what?
Like, do we need to character so when you determine it or not define? Or no?
You mean this? Like,
Yeah.
no, because both of them are going to result in it's not a point.
Right.
It does matter though when we get to here, because this won't tell us if we have a limit. And this tells us we have limits on the left and on the right, but nothing exists at x equals 2. So we know that we have an asymptote. That was our L5 lesson, right? Okay, so here's the rules. So we're doing continuity at a specific point. So like x equals 2 or x equals 6 or x equals 25. I don't know, but at a point. So all of the following criteria has to be true. So it can't be one. So the point has to exist. So you have a point. The point exists on the graph. That's step one. The limit exists. See, the limit, we have to be able to calculate the limit. Okay? And 1 and 2 have to be the same number. So in order for it to be continuous, the point has to exist, the limit has to exist, and they have to be the same thing. Okay, so you guys try this one right here.
Well, we end
I
up-
want to know if it's continuous.
We end up with an indeterminate.
Are you sure? He's right. We got an indeterminate. So is the point continue, or is the function continuous at x equals -1? No, because what happened? Right away? I don't even have to go any further because
Well, it doesn't even exist.
the point doesn't exist. So we know right away that the graph will not be continuous. It's if we got an actual number here, then we got to move forward. Does that make sense to everybody? Like, it's not continuous if the point doesn't exist. All right. Okay. Given this function, and this is a weird one, and this should be is. Let me flag that for another thing I have to fix. Is the function continuous? So weird, but it says, okay, I've got this rational function happening here. Everywhere my domain is infinite, negative infinity to positive infinity, except I don't want it to exist at -1. Okay, great time. But at x equals -1, I'm telling you that the function is a constant function and it's a point of 2. So if you look at this graph, it has this one single dot. So this, with this domain, is that little point right there. It's weird. We've probably never done that before. You probably haven't seen that before. But it's just a restricted domain on a constant function. It's weird, but we'll go for it. Okay. So if you had, so option 1 says, does the point exist? Yes, it does. So does the point exist?
Isn't it POD?
Nope. Where does the point exist? It exists at -1 and +2. It exists at the highlighted one.
Oh, I didn't see that.
I just went through. It wasn't something we're familiar with. Okay, 2, we have to ask if the limit exists. Does the limit exist at -1? Yes, it does. Where does it exist? Because we said that this one, if it got to a number, we had to keep going further. And this one has a number here. So we have to, this tells us to keep going. That tells us keep going through the list. Okay, so now we're going to calculate our limit. So we're going to do the limit of, oh, and I'm going to factor it for you guys, because it'll be okay. I'm going to factor it. It is, what is it? It's x plus 1 x squared minus 1 all over x plus 1. Now, if I were to put in -1, if I do direct substitution in there, is it going to work?
No.
No. So we're going to have to do left-hand side, right-hand side.
So we just cancel out the x plus 1.
Okay, you're right. Okay, I see where you're going. Yes, but if I did direct substitution into this, I would get an indeterminate. Or if I did direct substitution into this, I would get an indeterminate. So that tells me to keep going. And I factored it to kind of give you the next part. So limit as x approaches -1, those cancel each other out. So I'm at x squared minus 1. Oops. I don't know why I made that bracket so big because I thought it had a denominator. If I substitute -1 in there, is it going to work?
0?
It will give us 0. Well, I guess I don't have to put that there. I can put that there. All right. So we know that the limit at x equals -1 is 0. Is the graph continuous?
No.
No. This is a 2. This is a 0. It is not continuous. Now, we had the pretty graph that we could have just, having a hard time here. I'm talking and not being able to spell. Continue. Not continuous. And that's because there's that break in the graph. And it's just nice that we already had the graph there, so it wasn't like shocking or anything, but you can do all of this without graphing it. You can do all of it with graphing it if that's a strategy that helps you, but you can do it all without graphing it. Okay. This example, we don't have a we don't have a picture. We don't have a picture. And again, it should say is the graph, or is the function continuous? So what am I looking for? What's
Things that are happening at x equals to -1 and around.
things that are happening at x equals -1 or around -1? That's a really good way to describe it. And I'm getting that -1 from this, because I know it's equal to -1 here. It's got to be greater than -1, but not equal to here. So I'm looking for something around that. Okay?
It's 3. It's the bottom 2.
Okay, so which function does -1 belong to?
So,
The upper one, because it has the equal to sign in it, right? So when I go to see if there is a point, does the point exist? I'm going to be substituting x equals 1 into this function here, because this has the equal to sign. This is where x would belong to. X equals -1 would belong to. Does it work? It does. So that's going to be 1 squared, so that'll be -1 and 3. So the point exists. Yay, the point exists. So that means I have to go further. If the point didn't exist, then we're done. We know the graph isn't continuous. So now we're looking at the limit of the function.
We're going to do left-hand side, right-hand side with 2 different formulas. Let's go.
Nice, good catch, good catch. So we know that we have different things happening as we come to -1. So we're going to do left-hand side, right-hand side of -1. So if I have a number line here and I have -1, we know x is less than or equal to -1. It's this function. So that would be on the left-hand side. And we know that on the right-hand side, so x is greater than 1, is going to be the function 3, which is just a constant function. Y equals 3 is just going to be a horizontal line crossing my graph. Okay, so the limit as x approaches -1 from the left-hand side, we are looking at the function x plus 2 squared plus 2. And we just did direct substitution in there. So what do we know that is equal to? 3. And then if we look at the limit as x approaches -1 from the right-hand side, we know that we're at function 3. So we know that the limit is 3. So what do we know the limit of this function is? 3. Because the left-hand side and the right-hand side are the same, maybe I should write it out in limit notation. So limit as x approaches -1 of f of x, because f of x is that whole thing together, is equal to 3. So we know the point exists at 3. We know the limit is 3. So is the graph continuous at x equals -1? Yes, it is.
So in pre-cal, we projected x. Now we're trying to find out y.
And that's really the big difference between calc and pre-cal. We did a lot of restrictions on the domain, but it's really hard. Like if you hadn't had all that work on the domain, it'd be really hard to look. I can't imagine doing both of these things at the same time. Like trying to do all your restrictions on your domain, oh, and do limits on top of that. I think our heads probably would have exploded. So that's it. That's all. You finished your first unit. Congratulations. Only 3 more to go.